Good morning and welcome back to chemistry. Today we are going to be looking at how to calculate Q. All right, using this equation, Q equals mc delta T. All right, Q, remember, is a change in heat of a reaction. Remember, Rxn is just an abbreviation for reaction. That's all. So we're going to be looking at basically using this equation to help solve for heat in joules or mass in grams or specific heat, which is C. Normally it's called C sub P, but C is just fine for my class right now for an introduction to chemistry. And delta T. Delta, remember delta means change in science, and T is for temperature. And the way we find delta T, we do temperature final, T sub F, minus T sub I, which is temperature initial. So temperature final minus temperature initial. Okay, so we find that, so we subtract that, and then we can plug that into the equation right here. All right, so this is a pretty basic equation that we use in chemistry, and specifically thermochemistry. All right, so you might be asking, what exactly is specific heat? Make sure, and remember guys, you should be taking notes, so have your notebooks out. All right, take notes on all of this, please. The specific heat of a substance, and it's different for different substances, which is why I gave you a few down here so you can kind of just see the differences. The specific heat is how much energy a substance needs to take into itself to raise the temperature 1 degree Celsius. Okay, so if you have 1 gram of a substance, you need to look at how much heat energy it needs to take in before it raises 1 degree Celsius. Okay, and that is what you're seeing here. All right, joules per gram Celsius. Okay, that is the unit for specific heat, and this is the C of part of our equation. Okay, so for water, which is what we're going to be using a lot, and you'll need to remember waters. Okay, water, liquid water, that's the L for liquid water. Okay, is 4.184. Pretty standard. It's well known. So it needs to take in 4.184 joules per gram Celsius in order to raise 1 gram of water 1 degree Celsius. So it takes quite a bit of heat. It takes more heat than everything else. Here we have water, steam, which is gas. All right. Steam is already hot. Okay, so it needs to take in less energy to raise itself 1 degree Celsius. So liquid water takes in more energy to raise itself 1 degree Celsius, but steam, already hot, only needs to takes in about half as much energy to raise itself 1 degree Celsius. But if you look at metals, which we know are really good conductors, aluminum solid and iron solid, they take in much less heat to raise themselves 1 degree Celsius. So you can see here that metals, all right, this is an evidence that they are good conductors. They are good conductors of heat, which is why we use metals to cook in for pots, because they conduct that heat so well to our food. All right, they take in much less heat. Okay, so the more insulating a substance, the higher the specific heat, the more able a substance is to conduct heat and electricity, the lower the specific heat. Okay, so I just wanted to kind of go over what specific heat was so you have a general understanding. All right. Okay, so we are going to do some calculations. So I'd like you to get out your calculator, all right? And I would like you to please write down the problems, okay? And then follow my steps. If you do what I'm showing you to do, it will go a lot easier for you. And I need you to try these problems, because you won't know if you truly understand unless you try them yourself, okay? So, example 1, please write this down. How much heat is required to warm 275 grams of water from 76 degrees Celsius to 87 degrees Celsius? How much heat? Okay. So first, we need to figure out a few things. What are we solving for? How much heat? So we are solving for heat here. All right. Heat is our Q. That's our Q right here. Okay. We have our mass. Our M for mass is right here. Mass. Okay. This is our mass. And with specific heat. Oh, what's our specific heat? Oh, it says water, right? So water, remember water from, you're going to have to remember this, okay? Water, 4.184, specific heat, okay? So we know water is 4.184, okay? Yes, you can technically put the units. I'm going to be a little more forgiving about units for specific heat because they're a little bit more complicated, okay? But it's joules per gram Celsius. Sometimes it's joules per kilogram Kelvin, so just keep that in mind, all right? So 4.184, so we have our C, okay? I should go ahead and underline. We have our mass right here, mass, specific heat. We're solving for Q, and our change in temperature right here, delta T, this is our delta T, all right, is right here. Okay, so from 76 to 87, this is our temperature final, this is our temperature initial, okay? So to figure out our change in temperature first, so delta T equals temperature final minus temperature initial, all right? Our temperature final is 87 minus 76, all right? And that will give us a positive change of 11 degrees, okay? So now we just literally plug and chug. That's it. That's it. So we have our Q. So Q, all right, and you can write lowercase or uppercase. It doesn't matter to me, really. We plug in our M, 275 grams, okay? Plug in our specific heat, 4.184, and we plug in our change in temperature right here, 11 degrees. And then you just plug and chug, literally. So we go ahead and let's see if I can tilt this so you guys can see. 275 times 4.184 times 11. And you should get, all right, there you go, 12,656.6. Now, what is the unit for Q? What is the unit for Q? Well, let's go back to our first page. All right, Q, when you do this, is in joules. Joules, okay? So this would be J for joules, okay? And then please box your answer. When I ask you to show work, I want to see you write out the equation. I want you to show me the numbers plugged into the equation and the final answer with units boxed, okay? So I want you to show me this whole thing when I show you, say, show work. This is what I want you to do, okay? To be very clear. All right, let's try a different example. All right, go ahead and take a second to write this down. All right, so we have phosphorus trichloride is a compound used to manufacture pesticides. A reaction requires that 96.7 grams of phosphorus trichloride be raised from 31.7 degrees Celsius to 69.2 degrees Celsius. How much energy will this require given that the specific heat of phosphorus trichloride is this? Okay, so let's go ahead and figure out what we have to do. We need to solve for something. So it says how much energy. So again, we are solving for Q. How much energy, how much heat, that means Q. Okay? Let's look for our mass. Our mass right here is right here. 96.7 grams. Okay? Let's look for C, our specific heat. It literally tells you. Specific heat of phosphorus trichloride is this. Right there. You don't have to guess. It's right there. And we need to look at our change in temperature. Sorry, there you go. We look at our change in temperature, and here are our two temperatures. So it's when it says from, this is always going to be our T initial, okay? And 2, this is going to be our T final, okay? So that's our change in temperature right there. So let's go ahead and do the change in temperature first before we plug and chug, okay? So remember, change in temperature equals temperature final minus temperature initial. All right, so we have 69.2 minus 31.7, and that should give us a positive change of 37.5 degrees. Okay, so now we have the delta T ready to go. We are solving for Q, so we can just put that over here. And we're going to put on our mass. Our mass is 96.7 grams times our specific heat, 0.874. And you can put joules per gram Celsius if you would like to. And then multiply that by our change in temperature, 37.5. That's where we got right here. Okay? And again, plug and chug. Just go ahead and multiply that out. These are the easiest ones to do. We will have to do ones that where we solve for mass, specific heat, and sometimes change in temperature, which I will show you how to do. So we have 96.7 times 0.874 times 37.5. And you should get, okay, 3,169 and you go ahead and just round here, 34. I'm not worried about sig figs right now. All right, and again, because we're solving for Q, this is in joules. All right, so make sure you show me this work. Make sure you show me this work. It needs to be neat, and I need to see your work, okay? In chemistry, no work, no credit, period. I need to see this. All right, so go ahead and copy down number 3, please. Okay, a quantity of water is heated from 25 degrees Celsius to 36.4 degrees Celsius by absorbing 325 joules of heat energy. What is the mass of the water? Okay, so now look, what are we solving for? We are solving for what is the mass? We're solving for mass. So this is our variable now, okay? So let's go ahead and look at the rest of this. So Q is heat. It tells you right here. Here's Q, 325 joules. Okay, we're solving for mass. Our specific heat, well, what is the specific heat? It doesn't tell us. Well, it kind of does. Water, remember water? 4.184, okay? That's our specific heat. And our change in temperature is right here. This is our temperature initial, to temperature final. Let's figure out our delta T real quick, okay? So change in temperature, temperature final, minus temperature, initial, that should be a T, I apologize. All right, so final, 36.4 minus 25. All right, gives us a positive change of 11.4 degrees. Okay, so we figured that out first. So now let's just plug and chug, guys. So we take our Q, we put it over here. 325 joules equals M. Just put the M there like it'd be like an X in math, okay? Multiplied by our specific heat, 4.184, multiplied by the change in temperature, which is 11.4 degrees. And you're just like, well, how do I solve that? Basic algebra, my loves, basic algebra. We need to isolate the variable. So we need to multiply these first, okay? So let's go ahead and do that first. So 4.184 times 11.4, and that should give us 47 so M times 47.6976 equals 325. Okay, now we need to isolate the variable. Remember, if it's multiplied, we divide on both sides to get rid of that. So we divide by the same thing, 47.6976, and the same thing over here, just like in algebra, just like that, 47.6976. That isolates our variable, M. So our M equals 325 divided by 47.6976. There we go. That's our answer. So let's go ahead and round to the hundredths just for simplicity's sake. So we have 6.81. Perfect. So 6.81. This is in mass. And remember, from our first, mass is in grams. So when you solve for that, grams. and then you may box your answer. Okay? Again, please make sure you show me this work. Show me this work. You need to write out the equation every time. That way you don't mess up where you put your variables. Okay? It's not that hard, and it will help you to remember the equation come term time and for finals. All right? Okay. So let's try another one. Go ahead and copy this down, please. A 500-gram sample of an unknown metal releases 6.4 times 10 to the second joules as it cools from 55 to 25. What is the specific heat? All right, so this time we have to look at what we're solving for. So our specific heat, we are looking for specific heat, so C is now our variable that we're looking for. Okay? Q, it gave us joules right here. All right, gave us joules for our Q. It gave us mass, right? Oh, it gave us mass, sorry, right here, 500 grams, right here. And our delta T is right here. So this from 55, that's our temperature initial, to 25, temperature final. Okay, there you go. So, no, I should underline this just to be consistent. Okay, let's figure out our delta T before we begin. Temperature final minus temperature initial. All right, our initial temperature is 55. I'm sorry. No, our temperature final. Oh, I apologize. Excuse this. 25 minus 55, which is a negative 30 degree difference. Okay? 25 minus 55 is negative 30. And keep that negative in there. Remember, temperatures can go negative. Okay? So we have our joules. All right. And remember, if you're uncomfortable using scientific notation, just take it out of scientific notation. 6.4 times 10 to the second is the same thing. We just take that and we move it 2 over. So we have 640. That's it, 1, 2. So that is the same thing. So I'm just going to use the 640 joules. It's easier to put in the calculator, but it's literally the same thing. Okay. So we have, and also I should point out that because it's releasing energy, it's technically a negative because it's releasing energy into the environment. So it's an exothermic reaction, okay? So we're going to put negative 640 joules here because it is releasing energy, not taking in energy from like the other examples, okay? So we also have our mass, which is 500 grams, okay? We're solving for specific heat, and we're going to plug in our negative 30 temperature change. Okay, so this makes it a little bit different because we have 2 negatives in here, which we hadn't had before. Again, if it releases heat, it's a negative joule, negative. Okay, and again, if the temperature final minus temperature initial is negative, keep that negative. It's the same thing. Notice that these will actually cancel out, just so you know. Okay, so what do we do now? We multiply these guys. So we have 500 times negative 30, all right, and that gives us negative 15,000 C. All right. We can put negative 640 here. Okay. And to isolate our variable, we divide minus 15,000. I'm sorry, divide by negative 15,000. And we have negative 15,000 over here. That isolates our variable. Specific heat. Remember, negative divided by negative is going to be positive, so be happy. So we have negative 640 divided by negative 15,000, and that gives us 0.043. Go ahead and round that. That's fine. All right. Now you can put joules per gram Celsius. That's fine. So goodness gracious, joules per gram Celsius here. That is fine if you want to include that that unit. All right. So there you go. Specific heat should always be positive, and those negatives right there, they cancel each other out in the last step to make this a positive answer. Okay, so just keep that in mind. Sorry I messed up here and here, but that's life, right? Make sure you show me all this work. Make sure you show me all of it. All right, let's do example 5. Go ahead and take that down, please. All right. So again, let's go ahead and define our variables. So this is how much heat is necessary to change 52-gram sample of water at 33 degrees into hot water at 110 degrees Celsius. Okay, great. So how much heat? Da-da-da, we're solving for Q again. Happy times. So much easier, right? We have our mass. All right, mass right here. Mass. And we have our specific heat. Where's our specific heat again? Oh yeah, that's right. It's water. Water is 4.184. You're just going to have to remember that, my loves. Okay. Oops. Yeah, whatever. That's our specific heat. And we have our change in temperature. So it's going from, so this is temperature initial to temperature final right here. All right. So let's go ahead and do our delta T first. Delta T, temperature final minus temperature initial. Okay. So our final temperature is 110 degrees Celsius minus 33. This will give us a positive change of 77 degrees. So we have that ready to go. So let's go ahead and plug and chug. We're solving for Q. Our mass, 52.0 grams. Times the specific heat of water, which is 4.184. And our change in temperature is 77. All right. So easy peasy plug and chug. All right. So we have 52 times 4.184 times 77. Okay. And that should give us 16,752.74, and remember, Q is joules. Box your answer, please. And again, make sure you show me all of that work. Okay? So yes, when you solve for Q, it's much easier, but it is very important to make sure that you can solve for mass and specific heat, and we'll go over change in temperature later. Okay? All right, guys. What I'd like you to do now is I'd like you to try these two on your own. Copy them down and then try them yourself. And we will review them in class. Okay? So take a second, copy these down fully. Show me all of the work that I'm asking for. Okay? Try it and then we'll talk about it in class. Okay? All right. Thank you guys so much. I hope this was helpful for you.